Refer to the definition of symmetric difference given above. Prove each of 47 through 52, assuming that A, B, and C are all subsets of a universal set U. Now, I actually put the definition below here, which says that given sets A and B, the symmetric difference of A and B, denoted A triangle B, is A triangle B equals A minus B union B minus A. You can also just say symmetric difference instead of triangle. We need to prove that A triangle A complement equals the universal set. Now, I'm not going to use an element proof for this proof. I'm actually going to use the set identities, which there are, 12 of them here. But I think it will be a little bit easier to prove that A triangle A complement equals the universal set using the set identities. Now, the first thing we're going to want to use is the definition. The definition says that A triangle A complement equals, well, we're going to use this expression, but everywhere where you see the letter capital B, we're going to replace that capital B with an A complement instead. So this is A minus A complement union A complement minus A. Notice the difference between the definition and how we're applying the definition to this expression here. Now we have some more operations to work with here. For example, this set operation, the minus, can be unpacked using one of the set identities, which is the set difference law, which says that A minus B is the same thing as A intersection B complement. So I'm going to apply this rule twice, starting with this first parentheses. And this is true by set identity rule number 12. And this is true for set identity number 12. And we can apply set identity number 12 again to set identity number 12 again to this set minus operation here. Next, I notice here we have an A complement complement. And there is a law for this, the double complement law, which is rule number 6. So now we have this expression. Now, A intersection A is equal to A according to the idempotent laws. A intersection A equals A. And we can actually do the same thing with A complement intersection A complement. Even though this is not the same thing as A intersection A, it's still in the format of the formula within the law. The law is more of a formula, meaning that it doesn't matter what set this is and what set this is. If they're the same sets and you're taking the intersection between the same sets, then you end up just getting the original set. So A intersection A is just A. Let's go back a few steps. So let's first apply the idempotent law to A intersection A. Now the idempotent law says that A intersection A equals A. That's rule number 7. Now we can actually apply rule number 7 again to this A complement intersection A complement. Now notice that there is a difference between these two, but the law is more of a formula. This A can be any set, including A complement. So long as you're taking the intersection of a set with itself, you're going to get that set as a result, according to this law. So this is the same thing as A union A complement. And there's a law for that, which says that A union A complement is equal to the universal set by the complement laws, which is rule number 5. And that is the proof. We started with A symmetric difference A complement, and we used the set identities along with the definition of set difference to prove that this set equals the universal set. Thanks everyone, and I'll see you in the next video.